EP1200 Introduction to Computing Systems Engineering. In this first video part of the course, I will cover both combinational and sequential logic. Some illustrations in this material has been collected from the book The Elements of Computing System by Noam Nissan and Sharman Shokal. Let's start from the basics, the Boolean logic. This will go from simple NAND gates to any logic gate. Boolean algebra is an algebra of logic. There are some elementary Boolean functions that you might be aware of, such as not x. For one bit input variable x, it means simply that if x is 0, not x will be 1, and vice versa. And states that if both inputs are true or 1, then also and x and y will be true or 1. Or means that if any input is true, then the output will be true. NAND is the inverse of AND, so that the output is true if at least one of the input is false. There are two forms of expressing Boolean functions. One is a truth table, the one that we saw on the previous slide, which expresses input-output relationships. And another way is to give a functional expression, which often is simply if you want to do computation and also to put in print. Here's an example. A function that takes 3 input variables and computes one function, which is x or y times not z. So the expression is very simply put in a single line, but the truth table has to be computed for all possible inputs. This means that for 3 different inputs, each one taking 1 out of 2 values, you get 2 to the power 3, meaning 8 different inputs for this function. You can easily convince yourself that the truth table and the functions agree with one another. It's possible to list all Boolean functions of 2 variables. With input variable x and y, we get 16 different combinations. And you can see here that these are enumerated from 000 to 001, and then binary counting up until we get 111, which is the 16th variant of output that you can get from these different input values. Each line corresponds to a specific function. Like the first one corresponds to a constant 0, while not y corresponds to the line here. We see that it is the inverse of the y input. The Boolean algebra got its name from George Boole and wrote a book called A Calculus of Logic. He showed that given some function like NAND and a truth value like false, you can compute all the functions that we had in the previous table. So we can build a not a using NAND a and a. And we can get the true value by taking not of the false, and so forth. By building some functions, we can use them to get other functions. If you're familiar with the De Morgan's law, you could apply that and instead use nor and the truth values such as true or false, and in the same manner build all the logical functions that we had in the table in the previous slide. Let's move on to counting with binary representation of numbers. We will look at adders, and then we will look at the full arithmetic and logical unit that's needed for the hacker computer. If we take a quantity, we can represent that in decimal numbers from 0 to 10, because we have 10 quantities here, 10 asterisks. But of course, the representation of the number can be also expressed in binary digits. If we build hardware, we're always limited to how many bits our numbers will be. If you take a number which consists of 3 bits, then you only can represent up to 8 different values, numerical values in that register. If you continue to count, you get an overflow, that the number will wrap around and does not represent the actual quantity that you want to capture. It's also possible to represent negative numbers in binary. We talk about the 2's complement, which means that all positive numbers start with a 0 and all negative numbers start with a 1. So the most significant digit in the binary number represents the sign. You can get a negative number by taking not of the number, meaning that each bit in the number will be inverted, and then you add 1 to that number. Then you get minus x. Here's an example. X is 0, 1, 1, 0, which corresponds to 6 in decimal numbers. We invert the bits in x to get 1, 0, 0, and 1. Now we have to add 1 to that number, so we get not x plus 1, which is 1, 0, 0, 1, plus 0, 0, 0, 1. If we add them, we get 1, 0, 1, 0. So we see here we started with 6, and we ended up with minus x, so this is correct. This definition is important to remember when we look at the ALU later on. A simple way to convert a number is to leave all the trailing zeros and the first one intact, and then flip all the remaining bits. So for instance, if we take minus 6 here, we would leave the trailing 0, 0, we would leave the first 1, and then we flip the remaining bits. So we flip this to a 1 and flip this to a 0. So we get 0, 1, 1, 0, and this corresponds to 6. And with this convention of representing negative numbers, subtraction works very easily. 2 minus 5 is simply 2 plus minus 5. This is 2. This is minus 5, as you have it here. And then you do bitwise addition with carry. So 0 plus 1 is 1. 1 plus 1 is 0. Carry 1. 1 plus 0 plus 0 is 1. And 0 plus 1 is 1. So this is 1, 1, 0, 1. And that corresponds to minus 3, which is a result that we would have expected. Now it's possible to build an adder chip, very simply. For this course we use 16-bit numbers in 2's complement. We will not build the 16-bit adder from simple gates. We will have a hybrid element that we call a half adder and another element that we call a full adder. The half adder adds 2 bits and the full adder adds 3 bits. Then we'll use those to build the full 16-bit adder. The half adder takes 2 inputs. So it creates the sum of the 2 bits that you have here, and then you get a carry number from in addition. You can see these as truth tables. So you can see that the half adder can be built by 2 simple logical gates that you had from the previous part. The full adder takes 3 inputs. Here we're going to use that A and B are values from that we want to sum, and C will be the carry bit from a previous stage. And it has its own truth table, which allows it to be implemented from half adders. Given those 2 building blocks, we can build a full 16-bit adder as an array of those blocks. We now come to the ALU of the hack platform. This is a large complex circuit that takes 2 16-bit inputs and creates a 16-bit output. The function that the ALU will perform is set by 6 different control bits. The ALU also generates 2 status bits. One which is true if the result coming out here is 0, and one which is true if the result coming out here is negative. The functions that the ALU can compute are all the arithmetic and logical functions that we can think of 2 input variables x and y. This is the definition of the working of the ALU. You can see it as a large truth table in a way. It's interesting to see how a particular function is being executed by the various control bits. So if you take here, for instance, a constant 0 coming out, then it's created by setting this zx control variable to 1, so x is 0, and not to negate x. Then also y is set to 0 and not negating that. Then f is x plus y, so we add 0 to and 0 together, and then we do not negate the output, and therefore we get the 0. If we look at minus 1 instead, we set x of z to 0, and then we negate that. That means that all the bits in x will be flipped, so we get 16 ones being the value of x. Then we put y to 0, we do not negate it, so it's still 0, and then here we add all ones in x to all zeros in y, and then we do not negate the output. That means that we have an output value which consists of 16 ones, and that in 2's complement corresponds to minus 1. And then you can work through the whole table and see that indeed, if you set the control bits as follows in this table, you get the different functions performed by ALU. Next part is sequential logic. This includes registers, random access memories, and program counter. The combinational devices operate only on the data, so they provide calculations like NAND of 2 values, or addition of 2 16-bit numbers, or any of the functions in the ALU. But there is an inherent problem in the combinational. You don't know when you can trust the output. The ALU will have many internal gates, and if you provide 2 16-bit numbers x and y, how do you know when actually the ALU has computed the output, the function that you would like it to do? Sequential devices are different. They operate on data, but they also have a clock signal, so that the output of a sequential device will change with the clock and remain stable between the ticks of the clock. We use them to build storage and for synchronization. The low-level behavior of this sequential gate is tricky, so we assume that we have a data flip-flop, a 1-bit device that ticks the input to the output with every clock tick. We're not concerned with the implementation of the DFF. We take it as given in this course. Given the data flip-flop, we can build higher sequential chips from that one, just as we built the ALU from just being given a NAND gate. Let's look a little bit at the clock. It has 2 states, what we call tick and tock. Could represent them as a 0 and a 1, and 1 tick and 1 tock constitute 1 cycle. This is the frequency that will determine the speed of a processor. When we talk about clock speed, it's really the clocking of the sequential gates in a computer. In real hardware, the clock is implemented by an accelerator, but in the hardware simulator, the clock cycle is generally manually by clicking and moving the state forward, or automatically by the test script. The data flip-flop takes an input value and then clocks it out to the output. So that means that at time t you have an output which was the input at time t minus 1. So the input and the output can be different, of course, which is not the same thing as in a combination circuit. If you had a 0 as input to a NOT gate, then you immediately had a 1 at the output of it. This is a fundamental state-keeping device, and this is enough for us to build registers and RAM. The memory devices that we will come and build with the DFS require many flip-flops, but they will be regulated by the same master clock signal. This little triangle in the symbol for a chip means that it's being a clock device. You don't have to be concerned about the distribution of the clock signal out to the circuits, but we know that this is a time device. So how do we build first a 1-bit register? Here's a definition of it up in the corner. If we should load the input, then the output in the next time instance will be the input at that previous time instance. And if we don't load an input, then the output will remain constant without changes. So you can see that this stores the output value. As long as we don't load a new value, it will remain, the output will remain constant. So we start from the data flip-flop. At first thought, we might think that we simply take the output when we feed it back to the input. But this is a mistake, because what would the input be to the flip-flop? Would it be the output or would it be the input? So this won't work. Instead, we have to implement the 1-bit register by a flip-flop and a multiplexer. The multiplexer will choose whether the new input value should be latched in the flip-flop or whether the previous value should be fed back into the flip-flop. So if the load signal is false, it means that the output will always be fed back and latched into the flip-flop. But as soon as the load is high, this value will be ignored, and instead a fresh value will be taken to the max and latched in the data flip-flop. So given this 1-bit register, it's now very easy to build multi-bit registers. We simply just put them in parallel, where of a number of W bits, each bit will be stored in a 1-bit register, and they will all be controlled by the same load signal and the same clock. So if we want to build large memories, random access memories from this, we start with the register, which only takes one multi-bit number and stores it, and then we put those in parallel so we can store many multi-bit numbers. Now we need an address to say that if there's a new value coming in and should be stored, in which register should it be stored. And this is the random access that we talk about in random access memory. It also means that the output of the RAM could be any one of those values stored in the different registers. So we have to be able to select which value also should be the output value from the RAM. So by 8 different registers, we get a small RAM that can store 8 words, as we often call the numbers. And once we have those, we put them as module, and 8 of those modules become a 64-word RAM, and so forth. So this means that a RAM needs to take the values, the words, data words that should be stored. It will provide data word that's being read, and it needs to take an address to point to a register that should be the register of the output, or being the register where the input should be written. Depending if the load signal is false, then it's just reading out, or if the load signal is zero, if the load signal is true, then the input value should be stored in the register that is being pointed out by the RAM. This is the specification in the HDL for a RAM. And in the course we will have everything from 8 words, 64 words, 512 words, up to 16,000 words of data, each word being 16 bits. The final sequential logic component is a program counter. Its use will be apparent when we look at the hack computer architecture. It takes a 16-bit value in, and it generates a 16-bit value out. It has 3 control signals. If reset is true, then the value here will start from 0. If the value load is true, then the word provided on the input will be stored in the program counter. And if increment is true, then the value that's being stored here will be incremented. For instance, if we first reset and then continuously keep increment true, then we will see that the program counter will count from 0, 1, 2, 3, and so forth until it wraps around and starts from 0 again. This is the definition of it, and when building this chip it's important to consider the precedence of the control signals, because more control signals can be true at the same time. This chip can be implemented by a register chip of 16 bits plus some combinational logic that easily will work out. So in summary, it's possible to build advanced logical functions from simple elements such as NAND or NOR and data flip-flop. We need timed logic in order to trust output values and to store values. In this first part, I think you have experienced already the power of a modular building practice. Think, for instance, about the building up the RAM. By first building a 1-bit register, putting them into a 16-bit register, and then from 16-bit register building an 8-word RAM, and from 8-word RAMs up to 16K RAMs. You wouldn't like to build a 16K RAM out of data flip-flops directly.